And then the week after that, we'll be focused on learning about ground truth validation, simulation, and visualization as they're really related to image analysis. And so we'll be looking at those topics and sort of how does that fit together, because the first thing you have to do before you start analyzing all your data is really to look at it and understand the important things that are happening inside it and how you can decide what's relevant and what's not relevant so that you know what approaches might work best. And so that's sort of a new lecture for this year, so the slides for that aren't available yet. The next chunk will sort of be segmentation, and so this will go the basic segmentation, so how do you find sort of simple binary structures, what are the automated techniques available there, what criteria do you use to make sure that they're giving you meaningful information. And then after that will be the more advanced segmentation. So what other sorts of approaches can you use to identify more complicated structures? So the examples for this are kind of, if you're looking at ice cream images at really high resolution, you'll want to identify fat and ice as sugar, sort of among a number of other phases. But there's really a lot of different things that are mixed together that can be hard to separate. And so what options do you have in data sets like this? Then it goes to kind of the analysis part, which is sort of the what brings the quantitative components in. And so the first part is sort of how do you analyze single objects? And so if you have a single cell, how do you describe it? You know, you have area, volume, surface area, orientation, shape, deformities, all sorts of other metrics that you want to apply to it. How do those work and how can you calculate those? Next, we'll be looking at more complicated objects. And so when you don't have things that are simply or easy to model, how can you analyze those and what sort of approaches can you bring in? You then have spatial distribution. And so this comes in when you have really a lot of objects. And so if you think about, you know, a brain, knowing the exact shape of a single neuron isn't really important, but knowing how all the neurons are sort of placed relative to each other and how they're connected and how where there's really dense sheets and where there's much more further separated ones can be important information to extract. And so what sort of metrics are available for quantifying things like that? This also brings in this idea that I mentioned before with like alignment. And so how can you describe alignment in a meaningful way? The next part is really the big imaging. Of course, the idea is that all of the approaches we cover up until now will be adapted for scaling and easy to scale up. But these will really be the lectures that focus on how do you take these tools that we've sort of worked to understand and develop and apply them to real problems in order to solve or understand something. So the first one will be really statistics and reproducibility. And I assume everyone here has taken a statistics course before? Almost everyone, yeah? And does anyone feel comfortable saying what they think a student's t-test is? No one? Or one person? I mean, I won't make you actually say it, just would you feel comfortable answering a question like about a student's t-test, which is the most simple statistical analysis you can do, and you feel confident that you know what it is? Okay, we'll see. So that lecture will cover some of those ideas and how you can actually go from data to conclusions is probably a little bit exaggerated, but how you can interpret that data and understand the differences that you see between the groups and have some sort of meaningful statement you can make about it that's scientifically supported. The next will be sort of dynamic experiments. And so from the surveys that people filled out, it looked like one or two of you might be working on dynamic experiments where you have something that's changing with time. Is that how many people here are working on something like that? 1, 2, 3. Okay, so a few. Yeah. And so this will be, you know, what sort of different metrics do you need to quantify that? Because you want to be able to say, you know, how is it changing? How is it deforming or reorganizing? And what are reasonable ways to quantify that? and then a little bit on how do you need to design experiments so that you can measure what you're trying to measure. That, what we see quite frequently happen is that people say, yeah, it'd be really cool to see this happen, so we'll try doing an experiment and see what happens. And if you don't have any idea what you're doing, you can end up wasting a lot of time doing experiments that you then can't get any meaningful statements from. The last one will be sort of scaling up, or big data. And so big data is, of course, a very popular topic today. And this will be how you can really move beyond what you've done on single computers and use cloud-based or ETH cluster resources efficiently. And so for the tools that we use from the beginning, they have plugins that allow you to do this, but we'll cover in that specifically how that works and what sort of the general concepts of big data are, so that you can apply those ideas to the sort of work you're doing and incorporate it with some of the things that the major companies like Amazon, Google, and Yahoo are investing a lot of time in. The last part will be sort of the wrapping up. And so the guest lectures are still being finalized, but the first one will probably be on the 19th, and this will come from hopefully the Nexus Personal Health Center at ETH and the Scope M Imaging Center. And so they do lots of high content screening, and one of them actually was doing this at Roche before he came here, and so this is where they look at millions of cells a day to try to figure out which treatments worked on which cells and measure what changes happened there. And so I think that's quite a relevant application of this sort of big analysis, because you have lots and lots of samples coming in, and you need to analyze them, and you need to be confident that when your machine says something's interesting, that it's actually interesting, because if it's not, you waste a huge amount of time looking at kind of meaningless data. We'll then try to have a guest lecture with sort of machine learning and deep learning to sort of go into these approaches in a little more detail and how that fits with everything we've done so far. We'll have sort of a light introduction to that today, but that will go into more detail so you can understand those topics a little bit better. And then the idea would be on the 2nd of June to have the project presentations. And so there's a link on the site to sign up for projects, and I think next week in the class we'll talk about sort of specific project options you have. And so of course one of them is doing your own data, but we'll have a couple projects where we provide the data that you can try to analyze if that's interesting for you. Cool. And so now to go over kind of the very basics of kind of what is an image. And so this is probably the most important thing to define in a class called quantitative big imaging. And it's a pretty abstract definition. And so what we have is that it's a pairing between some sort of spatial information like position and some other information like a value. So the simplest way to kind of express an image is really just a list. And it's a list of positions and values. And so I think this is probably the most helpful way to think about an image, is that you just have this kind of list of points that makes up your image. A lot of times when you're dealing with 2D images, you then have this as sort of a matrix or a grid where you show the list of values organized in sort of the pattern that makes sense for it. But this is only one specific type of image, and an image itself can be many, many different things. And so I think it's important to have this separation, because this is just really one instance of it. And so your camera takes this where there's RGB values instead of an intensity value, but it's still a 2D. It's still a link between a position and a value. And so now looking at 2D intensity images, so what you normally measure in experiments are these intensity images. You don't typically get color images out of experiments. And so here you have sort of all the different positions, and you color the position based on the intensity that you measured at your detector. And this mapping between the color here and the intensity you measure is purely arbitrary. So you could just as easily use sort of a completely different scale to show the same information. It has nothing to do with it. You can also shift the scale. So here is sort of a logarithmic coloring scheme for this image. And they're all representing exactly the same data, but how you present it can drastically change what structures you see inside of it. I mean, so if you look at this image, your eyes focus on sort of these three stripes, but if you look at this image, this is the most interesting point. And so how you choose these scales is quite important to make sure that you're interpreting an image well. And this is where you see a lot of problems in papers, particularly, that if you don't consistently choose these scales for all of your images, or you perform operations that change this differently for certain types of images, you can end up with results which are not very reliable. And so, if you're trying to find a tumor or something and you look at this image, you might say that that looks kind of like a tumor, but if you looked at this image, it would look perfectly normal. And so having these scales consistently presented is very important for understanding the images qualitatively well. Yeah, so like we mentioned, you can have sort of this scale, and what you can do is you can shift how you map this intensity into a color. And so here we have the intensity on the x-axis and the color it maps to on the y-axis. And that would be sort of a linear rainbow scale that we have here, where it goes from red to purple, and kind of a linear flashing across the hue axis. And here we then have sort of a logarithmic scale. And so the differences between 0 and 28 or so are huge, but the differences after 50 are very insignificant. And so depending on what you're interested in getting out of your images, you'll want to adapt these scales to make sure that it matches well. It's also important that these scales match sort of the physics of the problem that you're trying to understand. And so, when you measure sound, you use decibels. And decibels is a logarithmic scale, and so something that's 1 decibel louder is actually an order of magnitude louder. And so having a scale that matches your understanding for this works well, and the eye is not a linear scale. And so making something that looks good to your eye isn't necessarily the best representation to have for it in a computer. So now, moving on to kind of more exciting images, like 3D images, which we'll have sort of in the exercises today. The position, or the spatial component, rather than just being X and Y, now has a Z. And so the Z shows you sort of where it fits on that sort of third axis coming out of the page. You can also display it as a bunch of images, so you can see it here sort of displayed as a stack, where you have the Z1, Z2, Z3, and you can color it again in the same sort of way. So with 3D images, you still have the same problems that you have with 2D images in terms of determining what scale or what mapping makes the most sense. And this is called sort of a lookup table. But you have the additional complication that your image is 3D, and so if you're trying to make a 2D representation of it, it can be very challenging. Luckily today, for a lot of these things, there's 3D printers, and so you can actually print out these images and look at them and touch them and rotate them around yourself, and so some of the complication of trying to visualize a 3D image can be reduced and made more tactile. What you can also see in images, and this is also where sort of the standard images most of you are familiar with out of your phones come from, is this multiple values. And so with the 3D images, we have multiple dimensional sort of positions, and you can also have multiple values or channels in your image. And so if you say a 2D image, that means there's 2 sort of spatial positions. And if you say a 2-channel image, that means there's 2 values that you have associated with each point inside your data set. And so here, one of the examples could be you have intensity, and then you have transparency. And so if you want to show how sort of transparent an object is, that you can have those 2 channels that you represent in your data set. With color images, you then have red, green, and blue. And so each point has an intensity for red, green, and blue that it's trying to show. You can then move beyond this, so that once you have multiple channels, you can actually have hundreds or thousands of different channels. And so one of the areas where this is very important is hyperspectral imaging. And this is where you make an image where at each point in your image, you have an entire spectrum of information that you're collecting. And so if you think about sort of light, or the way that your eyes measure light. It's just recording 3 pieces of information won't perfectly match the color you're trying to see in your image. And so the color you have in your image is a wavelength, or a distribution of wavelengths at intensities that you're trying to see. And so if you want to represent that accurately, you need to have the entire spectrum, or as much of the spectrum as possible, to get that to be sort of measurable. And so with a lot of scientific techniques, this is very helpful for looking at small changes in images that you wouldn't see if you just focused on 3 or 4 different channels, that you really need the hundreds of channels to see the differences. In chemistry, which is where this example comes from, this is using sort of Raman spectroscopy, so that you take a spectra at each point. And this tells you about the chemical bonds that you're looking at that point in the image. And so you can see and identify sort of regions that are very fatty versus regions that have lots of DNA, or regions that have lots of protein, by looking at the makeup of these different peaks and understanding those spectra. And these are all images. But of course an image like this is then really difficult to represent, because how can you show 1,000 different channels of information inside of one image? It's quite difficult. So now, in terms of image formation, and of course this is just a basic introduction to this, so that, if you're very interested, you'll take classes on those ideas. This is just to have an idea of sort of where images come from. And what we have in almost every case, there's a few cases where you don't have an impulse, but almost every case this is how it works, is you have sort of an impulse or excitation in your image. You're then looking at some sort of characteristic of interest. You have a response of what's coming out, and then you have a detection system. And so all the different types of imaging, no matter what you're doing, can be broken down into these 4 categories. And so when you're looking at sort of a camera that you have in a normal image, the impulse is light, so either from sort of a flash or the sun or a light bulb in the room. The characteristics that you're looking at are sort of how, to be sort of on the surface, how much a given sample absorbs light or reflects light. To get more detailed, of course, this is involved with sort of electron shell levels and electron densities and how the wavelengths of light interact with it, but to keep it at a higher level, you can move there. And sort of the response that you have is that the light is sort of diminished or increased in intensity. And the detection system is then your eye, or if you're using a film camera, then this film, which is sensitive to light, or a CCD or CMOS sensor, which can see this light and quantify it and spit it out. And so with every type of system that we have, we can break it down into that. And on this slide, we show that for a number of different approaches. And so here, you have light microscopy, white light, electronic interactions, absorption, you have film or camera. But if you're doing sort of ultrasound, instead of having light, you have frequency sound waves. You're looking at molecular mobility inside the sample, and you're seeing reflection and scattering come out of that. And you measure that with a transducer. And so instead of having your eye or a sensor, or a CCD sensor, you have a transducer which can measure these vibrations. With atomic force microscopy, it's then even more different, but it's still an imaging technique. And so you have a sharp point, which is your impulse there. The characteristic you're looking at are sort of the forces on the surface of your sample, or the interactions between this sharp point and your sample. The response is sort of contact or repulsion, so this tip is being pushed away or pulled towards the sample. And you measure that with sort of the deflection of a tiny mirror. And so you have a tiny mirror that's where a light's being reflected off of it, and you can measure how much that's being deflected at each point. So I think this is sort of helpful to see where all of these techniques come together, and that even though the impulses and characteristics can be wildly different, they all follow the same flow, more or less, and produce images at the output. So in terms of acquiring images, you have different approaches for doing this. One of them is sort of the traditional direct imaging approach. And this is where visible images produced can be easily sort of interpreted. And this is like optical imaging or microscopy. So this is where Up until recently, you used your eye. You just put your eye in front of a microscope to look through the sample, and you can see something there. The sort of indirect or computational imaging is where the recorded information doesn't really tell you about the object itself. And so for those of you familiar with diffraction imaging or MRI or some of these other techniques, there's a measured signal, but if you visualize that measured signal directly, it wouldn't tell you much about the sample. You would need to transform it into sort of this real space so that you could interpret it. Today, the differences between these aren't significant because this is just one step on a computer. But before, when you were looking at samples manually, you'd have to look at a shape like this and try to determine, what are the spaces that you have there, what are the different orientations, and what could the sample at the end look like. But now this is all automatic. So yeah, for traditional imaging, you kind of have this light source, your object, some sort of lens that you're using. So in optical frequencies, this lens is then a piece of glass. But if you're looking at X-rays, then you have other components which make up this lens. You then have your imaging plane, which is sort of a transformed version of your image after this lens. And that you have this kind of traditional imaging model where you have some light source come in, a beam profile, your sample, free space propagation, optics detector, and then what you end up getting is this long sort of equations, with this one on the top and one on the bottom, sort of the fully expanded version of that. And the problem is you're trying to focus on your sample characteristic, and you have all of these other parameters that you need to somehow get rid of. And so that's kind of that's a lead into what we'll do in the next lecture, is sort of how can you get rid of all of these other factors that are coming from your imaging system or noise or sort of other sources, because ultimately you're interested in knowing the sample absorption or the sample reflectivity or some metric like this. You're not interested in knowing what effect free space propagation had. You're just trying to get rid of factors like that. And so this can be quite complicated and take a lot of time or fairly advanced approaches in order to get rid of it completely, but it's a critical step because if you analyze your output from your imaging system and you assume that you're analyzing this absorption, you can be very mistaken and you can do lots of sort of not very valuable work because you're analyzing things that are coming from your imaging system, not things that are coming from your sample. So sort of an idea of indirect imaging, you have sort of micro lens imaging. And so I don't know if you've seen these new things where you can sort of refocus images after you've taken them. So this is one example of that, where you take an image at one point in time with micro lens array in front of the sensor, and then you can refocus it afterwards because you collect all the information at all the different focuses, and then you can play around with it. You can do similar sorts of things with like atomic force microscopy or sort of these 3D approaches where you can actually measure not just sort of color or the information, but actually a height related to it. And so here you have a picture of a flower where you can actually see that surface and how it changes. Cool. So now to kind of talk about image analysis, which is getting kind of the core of the course. You sort of have this world of image analysis, and an image is a bucket or kind of a list of pixels. And so you have positions and values, and you have some sort of connection between them. And how you turn it into useful information will really depend a lot on sort of what background you have and what approach you want to take. And sort of the way this world is sort of divided up now, there's 3 different approaches you can have. So the first one is really the experimentalist approach. The second would be the computer vision approach, and then the final would be sort of the deep learning approach. And they're not completely distinct techniques, but they're very different in the approach they take for trying to do the analysis. And so the experimentalist approach is really problem-driven. And so this is where you have a sample where you have kind of a reality or model-based understanding of what you're looking at. And so with the example of bone and X-ray images, you know that when X-rays go through bone, the calcium in the bone is absorbing a lot of these X-rays. And so you can measure how much calcium is in the bone by looking at how much of the X-ray is being absorbed. And then you can go back and say, if this bone has osteoporosis, by looking at how much calcium is inside it. So this is really this experimentalist or model-based approach. You can also look at sort of cell counting and porosity because you know there's supposed to be cells inside and you're trying to identify them, or bubbles inside and you're trying to identify them. The second approach is this sort of computer vision approach, and this is sort of method-driven, and so this is where you have a bunch of tools that you understand very well. So you understand how your feature extraction or how your image model works, and then you adapt these features to try to solve problems. And so what that's usually focused on are looking at sort of finding edges or shapes like that in structures, or doing face detection. And so I think, I'm not sure if it, there's, so if you have a tool like this shows you how you can do sort of face detection in using these features that you've generated that then look for objects that look like faces or look remotely similar to how you define faces to look. And then it's not really a physics-based approach because you're not thinking about how the light reflects on your face, you're thinking about what structures could make up a face and how you find things inside it. And so today this is such a standard approach that you can run it in a web browser in JavaScript. And so it's not something that you need to reinvent. There's tons of tools available for that. You can even show things like this where it shows you how likely it is that each point belongs to a face. So you can get much more detailed information out of it. Then the final example for this